good morning to all of you. So let me start with thanking the organizer for giving us the opportunity to present our our approach of sustainable steelmaking. I'll give the presentation into three parts. First part, some global picture, then some Indian perspective, and then what we are doing at Tata Steel. So just to start, let me give you a very brief intro of Tata Steel. So we are a 34 million ton per annum capacity global steel maker with Indian production capacity of 19 million. So we have presence almost all over the world. And we are Asia's first integrated private steel company established way back in 1907. So this is our Indian operation. We are kind of 19 million ton capacity with more than 65,000 people working and a turnover of more than 91,000 crores rupees. So this is our product range and all. I'm just keeping it because our main focus is decarb. So this is the kind of the overview of my presentation. So coming to the CO2 emissions, overall perspective, why it is important for steel industry and what we are doing. So just let us concentrate on this part. So overall emission from different sector, if we see, the industrial sector is contributing 34%. Steel is itself alone is contributing the 8.5% of the overall CO2 emission, what is happening globally. So you can understand, steel is accounting for the single largest CO2 emitter from industrial sector. No other industry is emitting as much as CO2 as steel is emitting. So it is a really big volume of CO2 we are emitting. I'll show you some data of that as well. But also you have to appreciate this fact that steel is pivotal for our human civilization. We don't know any other material as omnipresent. Of course, cement is there, as omnipresent as steel as a material. So it is touching everybody's life in some way or other every day. So we cannot get rid of steel, at least in the foreseeable future. So steel will be there, and the way the process itself is existing, it will be producing CO2. So we need to have strong strategies around decarb steel. So before going into the details of the decarbs, let me just put these slides. This is a known slide. This is an intergovernmental panel of climate change has depicted 4 pathways to show that representative concentration pathway, they call it. So how these things look like. This red line, which is RCP 8.5, is a business as usual line, where the CO2 concentration will increase up to 1200 ppm by the end of the century. And this corresponds to a overall increase in Earth's surface temperature by 4.3, which is as depicted by the scientists, is a really bad situation. And let us better concentrate on the RCP 2.6 line, this green line, which is a desired line for us, where then the increase in surface temperature can be contained by 1.5 degree or so. If you see this line, what is showing that the concentration of CO2 will increase, and then beyond 2040, it will actually start decreasing. So let us keep this data in mind, that CO2 will increase. It is already almost at the threshold, so we are almost at the 400 plus ppm level. We have few margins to cover, and then it should really reduce so that we can ensure that our surface is not getting warmed beyond 1.5 degree centigrade. So just a quick glimpse on how the steel is produced. So primarily the input in steel making is iron oxide. So there are several routes. Of this, let me take this one. This is the most popular route. Around 70% of the world steel is produced through this route. This is called BAF-BOF route, where iron oxide is reduced here, and then hot metal is poured into this oxygen converter to produce steel. The typical carbon footprint, typical CO2 footprint of this process is 2.5 ton per ton of crude steel. So you can say that we are producing more CO2 than steel actually, 2.5 times CO2 than steel. And there are other processes, kind of this process with gas-based DRI, natural gas-based DRI, having a kind of CO2 footprint of 1.5 ton per ton of crude steel. Not I would say not a very globally implemented process volume-wise, but yes, this has significant opportunity to reduce CO2. And of course, if scrap is available, if somebody has reduced that iron oxides for us and kept it for in some past in the time, so we can use that scrap and produce steel. That will have a substantial less amount of CO2 footprint, 0.7, 0.6, 0.7 around. So you may ask one question that 2.5 really looks big. Maybe the process is very inefficient. It is not designed properly. But let me assure you, this is a commercially viable process and going on for centuries. So people have done plenty of work, plenty of research has gone already into the process to make it very efficient. This is very close to the theoretical limit of fuel utilization. So it is not very inefficient process that the CO2 is so high. Only thing, this carbon what we are using primarily for the reduction and the thermal purpose, can we get rid of that? Can we, whatever CO2 coming out of this process can be processed some means, is a way out for steel. So just to give you a global picture, so if 8% of the global emission is from the steel, then just why can't we let it get absorbed by the environment? So if we just give a back of the envelope calculation, we need kind of 2 times the area of India as rainforest to absorb all the CO2, which is kind of impossible to do in present time of say amount of steel production. We'll show you in the subsequent slide that steel production is bound to increase. So then problem will be much more severe. But this is not an unknown problem to the world. This problem has already been appreciated early 2000, and people around the globe have started working. So here is a glimpse of different big consortium working across the globe. So Course 50 is a Japanese consortium where more than 20 organizations, almost all Japanese steel plants are involved, almost all Japanese universities working in metallurgy is involved. So very big consortium working from 2005 onwards, and already they have spent more than 2,200 crore of rupees in doing pilotings of different technologies. So their target is to reduce CO2 footprint from the blast furnace process by kind of 25–30%. So by saying this, I want to emphasize that you see the magnitude of the problem and the difficulty of reducing the CO2 footprint, and the kind of involvement is required. Similarly, this is a ULCOS program, this is a European program. So 15 European countries are involved. Several partners are there, and this is their budget only for piloting and lab-scale experimentation. We are also part of this, but then this is also a huge amount of fund already spent and huge amount of manpower already involved. So another good example, this is a recent example of hybrid technology. Here, this consortium has shown that steel can be produced at a footprint of 20 to 25 kg CO2. But of course, with a input of very green electricity, very high quality iron ore, etc. So here are a few other examples from like Arcelor's, Salcos. So there are several such examples. And many efforts are going on across the globe. So just to now coming to the Indian perspective, how it will look like in India. So here I would like to show you one thing, that this is a prediction for the steel demand of the globe, and this green patches, these are for Indian demand. So there are two kinds of prediction. One is standard policy scenario, which is business as usual scenario, this is sustainable development scenario. And both the scenarios, one thing is clear, that amount of steel will be produced in India will be substantially high. So as it is kind of predicted that by 2050, say, we'll be producing 500 million ton of steel, as against our present level of, say, 100, 110 million ton of steel. So it will be fivefold more. And if given a footprint of 2.5 ton per ton of crude steel, you can imagine how much extra CO2 will be releasing. But at the same time, we have to comply to our Paris Agreement, and we won't be able to allow to release so much extra CO2 in the ambience. So our problem is a little bit more severe because our production, inevitable production increase in steel. So adding to this problem, this is a typical Indian situation. If we see our raw material available, iron ore deposit available, is not very superior quality. It is generally very high alumina. And alumina poses certain problem in steel making, which essentially increases the amount of fuel demand and also subsequently the CO2 generation. And as we are mining more and more, our iron ore quality is depleting. So this alumina or the gangue content in the iron ore will be increasing, and that will pose additional problem on our CO2 numbers. So in one way, the production, and the other way, the depleting source of iron ore, both the way, this will put a challenge for us. So here I am trying to depict a scenario where we're producing 10 million ton of steel in a BOF route, which is most popular, and we have to achieve zero CO2. How it will look like in Indian context. So if at all we can able to do that, and what we will be doing here, that we'll be putting hydrogen into blast furnace to the extent possible, and whatever cannot be taken care of, the CO2, we'll be making that, say in a hypothetical situation, we'll be making methanol out of it by putting hydrogen, and the electricity requirement will be all green. Then this will be the scenario that will be, for this 10 million ton steel plant, integrated steel plant, will be requiring around 18.3 gigawatt of electrolyzer capacity. The cost of this electrolyzer as of today will be 90% of the otherwise cost of the 10 million ton plant. So it's a huge cost of the electrolyzer that we have to spend if at all we can. I'm not telling that the amount of area requirement. The area requirement will be also huge because hydrogen generation, the safety norms, and the space, for the complying to the safety norms, the space requirement will also be huge. Just assume that is available. Then also the capital cost of the steel plant will be 1.9 times than the usual cost. The green electricity requirement will be kind of 0.5% of the whole renewable capacity, what is projected which is projected available at mid of the century. So this is also a huge requirement. So we'll be requiring kind of 3 million ton per annum of hydrogen, kind of projected capacity, or 10% of the projected capacity, which will be available in India by mid-century. So this is a huge amount of resource we'll be requiring if we just want to zero CO2 footprint of a 10 million ton integrated steel plant. And also, at the same time, you have to just think of disposing this 14 million ton of methanol we'll be producing, which will be kind of 50% of the Indian demand of methanol. So which is a kind of impossible task. But yes, this challenge is very severe. So just take another example. Just assume that the way I have shown that hybrid technology, which is kind of right now demonstrating as a 1 ton per hour scale, is having a CO2 footprint of 20-25 kg. Just imagine that can be scaled up to a 1 million ton per annum hydrogen DRI technology. So what it will look like. So kind of in our Jamshedpur works, where we are producing around 11 million ton of crude steel, where our electricity demand is 500 megawatt. So if we want to produce just 1 million ton of H2DRI, our requirement of electricity will be equal to that 11 million ton of present land. So it is a huge electricity requirement. Land requirement will be 5.5 times of the football ground. We also need, since we need such a big power, we need improvisation of the grid and also hydrogen at an economic price. Of course, at volume and at economical price. So these are the challenges we'll be facing. And we really do not have a very straightforward answer to this. So these are one-way challenge. Another way is a huge opportunity for us to do research, to pilot something and come back with some breakthrough technologies which can change this scenario. So just on the boundary, what I will say, we have set our target already, that Prime Minister has announced that net neutrality by 2070. With steel, for steel also, we need to comply to this target. We have to substantially reduce our CO2 footprint. Just taking the clue from the COP26 announcement from by the Prime Minister. So these two things, that availability of the non-fossil energy and the 50% reduction of the energy requirement through renewable may be a good enabler for the steel industry. But our requirement will be much more, seeing that we'll be producing around 5 million ton per annum. Of course, this may be there will be, we can expect from this announcement that there will be some amount of policy interventions as well, which will encourage us to adopt some CCU, CCS kind of technologies. So now I'm just quickly giving you some of our Tata Steel's effort here, what we are doing. So this is our target. So we have already announced that by 2045, we'll be net neutral in our Indian operation. And by 2030, we'll be less than 1.8 ton per ton of crude steel. So this is a very, very ambitious target for any steel company of our volume and with the existing plant. So I'm now just showing you some of the glimpse of our research, what we are doing to achieving carbon neutrality and what we are doing in leveraging low quality raw material. So I'll quickly glance through this. So in Tata Steel context, most of our steel is produced through blast furnace route, 92%. And if you see the amount of CO2 coming from the different processes, 70% of the CO2 is coming from the blast furnace process. So our effort of decarb is mostly focused around blast furnace. So blast furnace is kind of the epicenter of the problem. So we are doing plenty of research, plenty of work around blast furnace. So this is a kind of busy slide, what kind of collating what all we are doing in to achieve carbon neutrality from the iron making process. So if we can categorize this into two parts, one is carbon direct avoidance, and the second part is carbon capture and utilization. So host of work is going on. I'll give you a glimpse of this A, B, C, D. So where we have done a certain amount of, we have successfully proven things in lab scale, and now doing some amount of piloting, and the results are encouraging. So coming to this hydrogen production, so globally, if you see the general trend for a steel industry, where the hydrogen is sourced, it is through electrolyzer, little bit of through biomass gasification. So this is the trend. Where we are trying something different. We are kind of reconfiguring this chemical looping combustion in such a way that the gas, BF gas from the steel mill will be used to generate hydrogen. And we are expecting, we are kind of almost completing this piloting as well. So we are expecting this, our 15 to 20% of the hydrogen requirement will be sourced from this technology when it is available at scale. So, okay, I'll be a little quick here. So second thing what we are piloting is for syngas generation. So I'm just skipping it for the paucity of time. So this is one good thing in a blast furnace if you can get rid of carbon as a reductant. So what we are trying here, we are trying to inject hydrocarbons through the bottom part of the furnace as natural gas or say coke oven gas or even pure hydrogen, so that the part of the carbon can be replaced. So we have done extensive lab scale studies, and then we have injected coal bed methane into one of our blast furnaces. We have done a kind of 1 month trial. This is first time in the world we have used coal bed methane for injecting in blast furnace. So we are also preparing our furnace to inject biochar, which is carbon neutral, which is CO2 neutral carbon source, and also we'll be demonstrating hydrogen injection in blast furnace this year. Piloting example from us, we have successfully piloting now this 5 ton per day CO2 capturing, taking the blast furnace gas as an input. Okay, scrap is one such thing where, as I have explained you, is a substantially less CO2 because the oxide is already reduced. So we are kind of piloting at a 0.5 million ton per annum at Rohtak, Haryana. We are expecting to go 5 million ton by 2030, which will reduce our CO2 footprint substantially. So this is a flagship iron making process. We are successfully piloted now. Will be soon commercialize this. We call it Hisarna. But this low grade, I will not go into the details of the process. Where only point I will try to make that it can take very low quality iron ore. You don't need any coking coal, and also at scale, when the CCS technology will be successful, the carbon footprint will be 80% less than the blast furnace. So we'll be soon putting some commercial plants here in India. So I'll not explain anymore. So I'll just try to finish my talk by saying this: our destination is known. We have to be carbon neutral by 2070. In Tata Steel context, we have to be carbon neutral by 2045. But the path is unknown. We seriously do not know which path we will be following to achieve that. So if not anything, our journey will be very exciting. So by saying that, but yes, we have miles to go. By saying this, I will stop.